Hi, Tor Lacey here with a lecture about glaciers and climate change. Let's first take a look at our student learning outcomes. Through completing this module, you should be able to describe the role weathering, mass wasting, and erosion play in shaping Earth's surface, and can provide and identify examples of each of these processes. Differentiate between constructive and destructive geologic processes, and are able to explain the energy driving these processes, and can identify examples of each. Identify and interpret erosional and depositional landform features in photographs and topographic maps, and explain the causes of ice ages and glaciation. Glacial erosion and deposition has created very distinct landforms in mountainous regions and higher latitudes in North America. These landforms are still geologically new and relatively easy to recognize, having been formed in the last few tens of thousands of years during the last ice age. Glaciers form in places where more snow accumulates in the winter than melts away in the summer. After hundreds to thousands of years of net accumulation, the snow will compact under its own weight, recrystallizing to a denser form called glacial ice. Gravity will act on this mass of ice, causing the glacier to slowly move downhill. The glaciers we see today are associated with Earth's most recent ice age, the Quaternary, which started about 2.5 million years ago. Two main types of glaciers are recognized: alpine or valley glaciers and continental glaciers, also called ice sheets. Alpine glaciers, also called valley glaciers, are so named because they are found in alpine settings, alpine being another word for mountains. The name valley glacier is also appropriate because they are contained within valleys in the mountains. Continental glaciers are not contained in a single valley, but instead cover all or part of a continent. Today there are two continental glaciers, one covering most of Greenland and the other covering Antarctica. If you're interested, here's one way to visit a continental glacier. Glaciers are similar to streams. They are made of water, albeit frozen, and move downhill under the influence of gravity, eroding and transporting sediment. The erosional power of glaciers shapes the landscape into destructive landforms and also acts as a constructive geologic force by creating landforms through deposition. In contrast, a glacier moves much slower than a stream, less than a foot per day versus hundreds of thousands of feet per day for some streams. Glaciers are much thicker and heavier and therefore have greater erosional power, being able to carry truck-sized blocks of rock suspended in ice. Finally, glaciers are only found in cold places, while streams can be found almost anywhere on the planet. Glaciers are the most powerful erosional agents because of their tremendous weight. Proof of their erosional power can be found in the form of glacial erratics, car-sized boulders that glaciers have plucked or ripped away from the bedrock over which they once flowed and were deposited when the glacial ice melted. As a glacier flows downhill, it accumulates progressively more rock fragments, which in turn do abrasion to the bedrock over which the glacier is sliding, leaving behind distinctive glacial grooves. Landform features formed by glacial erosion and deposition can be organized by the type of glacier that made the landform. We'll start with those formed through erosion by alpine glaciers. Preceding the Quaternary Ice Age, alpine regions contain well-defined V-shaped valleys. As the climate cooled into the Ice Age, winter snows persisted through the summer and snow began to accumulate in higher elevations. When these piles of snow became thick enough, they compacted under their own weight to form glacial ice, which then flowed downhill to create the erosional features we can observe today. Some of the most common erosional features formed by alpine glaciers include glacial troughs, also called U-shaped valleys, horns, cirques, tarns, arêtes, hanging valleys, and paternoster lakes. This is Yosemite Valley, here in California, one of the most famous U-shaped valleys. Once upon a time, this valley was almost entirely filled by a glacier. You may have seen a horn before. Disneyland's Matterhorn ride was modeled after the glacial horn in Switzerland, which, like other horns, is a pyramid-shaped mountain that was shaped by glacial erosion. This photograph shows a couple of cirques and tarns. Cirques are found at the head of a U-shaped valley and typically have an amphitheater-like shape. A single lake at the bottom of a cirque is called a tarn. An arête is a very steep-sided ridge between two U-shaped valleys. Here's another photograph from Yosemite. Like streams, the main glacier in the glacial trough is fed by smaller tributary glaciers. These smaller glaciers are less heavy and therefore do less downward erosion. Consequently, the U-shaped valleys formed by these smaller glaciers are left hanging above the main U-shaped valley, since their rate of downcutting couldn't keep up. Waterfalls, like Bridalveil Falls in the photo, form when hanging valleys contain streams. Paternoster lakes are simply a series of lakes occupying the bottom of a U-shaped valley. Fjords are U-shaped valleys that have been flooded by rising sea levels. Some alpine glaciers flow all the way to the sea. As global temperatures rise and these glaciers melt and retreat, their meltwater enters the ocean, causing sea levels to rise and flood the U-shaped valleys. Domes form when alpine glaciers flow over especially resistant bedrock, eroding it into a dome shape. To summarize, A, before mountain glaciation, the area has a normal stream-dominated topography. B, the extent of the glaciers during mountain glaciation. And C, the area's erosional features after mountain glaciation. When glaciers flow to lower elevations or warmer latitudes, they will melt, depositing their load of sediment, which is called till. Till is typically a very poorly sorted mix of fine to very coarse and angular grains. In some cases, the till has been shaped into distinctive depositional landforms. Two common depositional features associated with alpine glaciers are lateral moraines and medial moraines. In this photo, we see the lateral moraines that formed as the melting and retreating glacier deposited its till. Lateral moraines can be used to estimate the maximum height and extent of an alpine glacier. Medial moraines form when two lateral moraines merge into one. Some common depositional landforms that form when continental glaciers retreat are terminal and recessional moraines, drumlins, eskers, and kettle lakes. While the origins of drumlins is up for debate, it is agreed that they form from the deposition of till beneath continental glaciers. Commonly, they are asymmetric in shape, with a steeper and less steep side. The steep side faces the direction from which the glacier advanced. Here's what drumlins can look like on a topographic map. Note the steeper and less steep sides, which in this case tell us that the glacier advanced from the north. Eskers also form from till beneath a glacier. They are different than drumlins in that they are considerably longer and form when a meltwater stream exits a glacier. Here's an esker on a topographic map. Earth has an ice age when global climate is cold enough that large ice sheets grow on continents. There have been at least four, one approximately 2.5 billion years ago, another about 700 million years ago, a third 323 to 300 million years ago, and the one we are currently in, the Quaternary Ice Age, which started about 2.5 million years ago. During the current ice age, there have been at least 18 glacial interglacial cycles, when glaciers have advanced and retreated in response to relatively rapid cooling and warming within the ice age. Why does Earth have ice ages? To answer this question, we need to first consider the geologically long gaps of time between the four recognized ice ages. Next, we need to consider the significantly shorter periods of time between the glacial, interglacial periods within an ice age. Plate tectonics, most simply and effectively, explains the long-term cycles of hundreds of millions of years separating the four recognized ice ages. In order for an ice age to occur, the continents must be positioned close to the poles, where it's cold enough for glaciers to form. Through the process of plate tectonics, this happens over the course of hundreds of millions of years. Plate tectonics also disrupts ocean currents, resulting in ocean circulations that can bring down global temperatures. The time-spanning glacial, interglacial periods within an ice age happens on a geologically short-term scale of 50,000 to 100,000 years. This rapid cooling and warming of the planet is far too fast to be explained by plate tectonics, so another mechanism is needed. The Milankovitch cycles were developed by an astronomer and use the variations in the intensity of solar energy reaching Earth to explain the relatively rapid warming and cooling that can happen to Earth. The Milankovitch cycles are based on three factors: precession, obliquity, and eccentricity. Precession is the wobbling of Earth upon its axis, in the same way that a top begins to wobble as its spin slows. It takes Earth 21,000 years to complete one full wobble or precession. Obliquity describes variations in the amount Earth tilts on its axis over the course of 41,000 years. Eccentricity is the term used to describe the variation in Earth's orbital path around the Sun, which varies from more circular to more elliptical on a scale of close to 100,000 years. When Earth's precession, obliquity, and eccentricity are combined, the result is that Earth receives significantly less or more incoming solar energy, also called insolation, from the Sun. In turn, there are relatively rapid fluctuations in global temperatures on a scale of 50 to 100,000 years. In the last 200 years, coinciding with the Industrial Revolution and the release of man-made greenhouse gases into the atmosphere, Earth is experiencing an unnaturally dramatic rise in global average temperatures, referred to as global warming and climate change. The rate of increase in global temperatures during this time far exceeds the change in temperatures related to the Milankovitch cycles. It seems very unlikely that Earth's living organisms will be able to adapt quickly enough to successfully evolve with this rate of climate change. This is the end of this lecture about glaciers and climate change. Thank you for listening.